Welcome, everyone. We're extremely happy to have you here for the grand final of our hackathon championship on AI and cybersecurity. We're especially happy that so many of you really made it to come here and that everything so far went smoothly. And we're looking forward to the next 24 hours of great fun and challenges. So, with that, let's begin.
Okay, so I think that all of you know us. Just a very, very brief introduction. So my name is Adam Dejic.
And I'm Franziska Böhnisch. We're both faculty at CISPA, and we're extremely happy to host you kind of in our halls now.
And today, actually, we have also with us CISPA team. First, our students who sit over there. I think we have them. Then raise your hands. So for today's hackathon, if you have any questions, you can just ask our experts, and they will happy to help you with all of these questions regarding technical aspects, tasks, leaderboard, and you name it. So apart from them, also we have our CISPA staff, STAM and communication teams. Also, please raise your hands. All of, okay, great. Okay, so please feel free to ask them questions regarding CISPA, regarding communication. Also, we invite you to also give interviews and contribute to this great event. And yeah, you know where you are. You came to CISPA. We are exactly in this building. We showed that to you every single time when we went to the regional hubs. So now you are here. And so briefly about CISPA. So we really grew very, very fast. We have researchers who work on security and machine learning, AI. So we are here in Saarbrücken. Probably most of you came from Frankfurt. We also guests from Paris. And so now you know exactly where we are. And here we have more than 750 employees at CISPA with many different nations. And overall, we have more than 50 faculty members, group leaders who lead their respective research groups.
And one thing that at CISPA we are very proud at, you're now working at AI and cybersecurity, and that's exactly the thing that we are working on here. And we're not only working on that, but we're working on that with extreme success. Because if you look at the CS ranking, the standard ranking for computer science research, then you see that for the category of cybersecurity research, CISPA is #1 in the world. And of course, if you want to contribute to such research, then you're more than welcome to look for opportunities. The students in our lab have already found this opportunity and do research with Adam and me on secure, private, robust, trustworthy, and interpretable machine learning. But of course, CISPA has many groups, many different topics. So if you're interested in any of those, just reach out to us and we'll make the connection that fits best to you. And so, is it time for the video now, or?
Also, we'll go through the awards.
Perfect. Then
So I think that's probably for most of you of big interest. What are the awards? So as you know, all the three top teams from local hubs in Paris, Vienna, Stockholm, Munich, Barcelona, and Warsaw came here to compete to become European champions in AI and security. So you are here to compete for this great award. So we have first of all, our sponsors, G-Research, sponsored the first two places. So the best team from today and tomorrow's competition receives 4,000 euros. Second team receives 2,000 euros. The third team, 1,200 euros, sponsored by QuantPy. And also we have for all other teams, 400 euros, also funded by CISPA. So we have these sponsors who also enabled you, especially CISPA, funded your travel to Saarbrücken, funded your stay here. So this is something that we are really grateful that we have this help from the companies, from institutions to help to organize such a great event. And then we know that all of you need a connection. So if you want still, please scan this QR code. The network ID is hackathon. So you'll be able to seamlessly connect to this network and hopefully everything works as planned. So give you still a few seconds to connect. If anything afterwards is still not working, please contact us. Our team will help you to connect.
And we'll send the information also over Discord, so nothing is lost if it doesn't work now.
So regarding Discord, you can also scan that and I think that most of you are on Discord already, but if you are not there yet, then please scan this QR code and join our Discord channel. So as usual, we'll announce all the tasks, all the PDFs with the tasks will be sent there. Information about how to solve the tasks, how to approach solutions will be also posted there. So please join the Discord channel to learn more about these aspects. And now, so we also have to go through the plan. So just that you know what is in front of you for the next more than 24 hours. So you already are here, you came by bus, great that you made it, and you also registered. And now we have this opening plenary session. So here, what is the main goal is that we'll go through the information regarding the hackathon, also information regarding the tasks. We have also a great speaker from Meta, so we'll also announce it very soon. And after that, at roughly 10:30, so of course, we might take a bit longer to discuss these tasks. We will start the hackathon. What is really extremely nice is that so Julian with our other administrators were able to also make this selection of the desks for you guys to be more fair. So just you you just select randomly your desk, and then you will be assigned to this desk. So there is fair distribution of the desk. The whole building is ours for this 24 hours. So we will find a spot for you to work on these tasks. And also we'll have snacks. If you want to eat anything, we have pizza from yesterday. Just let us know. Nobody should be hungry, okay? And then we have dinner at 5 p.m. in the lobby near the main entrance. And we have hacking through the whole night. Some of you ask if they can go back to the hotel. Of course you can. You might waste a bit of time. So of course, but if you want to take some rest, you want to just relax a bit, you can always go back to the hotel. There are many buses going through from this bus stop and other one at the university. So no problem to reach out back to your hotel. Now, on Friday in the morning, so tomorrow, we'll also have in the morning breakfast at 8 a.m. served here in the lobby. And then roughly at 10 a.m. we'll end the hackathon, so the coding will be closed. We'll close the scoreboard. And then actually, here is a small change to how we'll announce the results. So after we close the scoreboard, only one team member from our team can see the validation set results, meaning that the final results for the coding part. And then the first 6 best teams will be asked to prepare presentations. Each of the teams will have 6 minutes to talk about your solutions, how you solve them. Of course, we'll ask questions, not only us, but all of you. And then after these presentations, we'll let you go back to the hotel. There will be a bus here, and then you can go back, you can refresh before coming to the big party in a different location where we'll actually announce the results. So over there, we'll inform you who are the European champions and also respective other places. And yes, with that, we can now start. Also, actually, the jury. So we also have the finally discussions within our CISPA team and our technical team regarding the placement of the teams and the awards. So it will take us some time. So please help yourself in the meantime to go to the hotel, relax, and we will work on the final results to announce them at the end of the day on Friday. And
so with that, it might be a good time to share the video, right?
I think so.
So hi everyone, I am Thomas. I am research scientist at Metafair, and so in Paris actually. So it's not far from here, and I'm gonna be talking about how we do content provenance at Meta. So nothing is working. Oh, okay. Yeah, good. So what's the outline of the talk? So first, what is content provenance? Apparently, a lot of people, even in Meta, don't know what that is. The next, why is it needed? How to do it? And then I'll talk about our 2 works on pixel seal and text seal. And then finally, some outlook into the future. So what is content provenance? Since Meta AI models are now good, so and nobody knows apparently. I asked it what it thinks about it, and so content provenance by definition of Meta AI is the verifiable record of a piece of digital content's origin, authorship, and edit history, showing where it came from and how it has been changed over time. So why is it needed? So you probably heard about a lot of scams on the internet, of AI scams. For example, one great example, well, not great, but interesting nonetheless, is that on Amazon you can buy many more AI-generated books than actually the original books by the authors sometimes. For example, you can even buy Deadly Mushroom books, AI-generated only. On YouTube, you can watch live stream of Elon Musk selling crypto on hijacked channels, and you can see like actually people are watching it. So and sending fake Elon Musk crypto. So that's one side of content provenance that we would like to probably address, and that like a lot of people are focusing on. But there are also other sides of content provenance, which are more interesting maybe for Meta and in general for like applications that are not related to AI. So, for example, on Instagram, if you are a popular creator, people usually like to reshare your posts and get views on like non-original content. So we would want to track this and boost the original creators, not the ones that just try to piggyback on the good creators. Similarly, we want to potentially attribute the videos where they came from, which also has, for example, marketing purposes for Meta. So if you record something on your glasses, then you can get this tag and potentially also drive sales. So how to do this? So there is this thing called metadata. You probably heard about this like from 1960. And so all the cameras, all social networks, and even AI-generated content now has the metadata, which is also digitally signed, for example. And so can this solve the provenance? It's definitely, it can work on real content, AI-generated content. It's easily scalable, and anybody can publicly verify whether it's legit or not. So provenance solved. Thank you very much for the lecture. As well for inviting me for the lecture. And then, like, of course, this is not really the truth. We can just do a screenshot or remove the metadata, and everything breaks. So this is not the be-all and all solution. So can we do better? For example, can we use fingerprinting to do this? It's nice, but well, it works on real and AI-generated content. Both can be fingerprinted, stored in a database. This is not scalable, though. You have to have the database, and more content you have, like it blows up, and it's very difficult. And also, there is really not like this kind of a public detector that you can use. Usually, it's the company who holds the database. Maybe you can somehow do like distributed databases, but it's probably really not a thing. So we can also do a deepfake detector. Train a classifier to classify AI content or it's like scams and stuff. It's easily scalable. It's a simple classifier, but it doesn't really work, right? So the better the models are, the worse the classifiers are. And of course, you cannot make it public. Once you make it public, then everybody can exploit it. So can we use watermarking for maybe some saw the pun. Can we use watermarking to solve the content provenance? It is easily scalable. You have embedder and extractor, simple neural networks. Works on AI-generated content, but also if you make the watermark imperceptible, it also works on real content. You still don't have the public detector, right? Because if you open up the detector, it's a bit of a problem in terms of like, again, people can attack it and evade the scheme. Security through obscurity is not a great solution, but hey, it's at least 2 out of 3. So can we use watermarking? Can it be the solution? So how does a simple watermarking work? So in this case, the simplest, probably easiest to understand is the post hoc watermarking, where you have a content then the watermarker, which is usually a neural network, that gets some kind of a signature. It's just like a bit string. And it embeds it into the image so that ideally it's imperceptible. You don't want to change the image much. And then if you share this image, do whatever, edit it, post on social media, you can still recover the original message, so you kind of can trace the content. So this is great, but this is very easily attackable. So for example, one of the easiest and probably like very good attacks is diffpure. It's just basically taking a diffusion model, taking the watermark content, adding a bit of noise, and doing this one-step diffusion process where you just like remove the noise. And because the diffusion model is adding basically more or changing the image more than the invisible watermark, it will basically by definition will always have to destroy the watermark. Because the original watermark was like restricted in the sense of how much it can change the image. So instead, maybe can we do semantic watermarking? Could semantic watermarking be a solution? Basically, so we add a couple clouds. I don't know whether you can see it. Add a couple clouds, maybe a bike into the image, so so that this kind of semantic will carry the watermark. Okay, so there is like one quite old solution of semantic watermarking for diffusion models. How it works is that you don't start from like purely random noise, but inside the random noise of diffusion models, you inject some kind of a structure, and then you denoise this, from this special type of noise. You end up with an image which kind of has some semantic properties that come from that type of a noise. And then to detect the watermark, you basically do the diffusion process the other way around through the model. You get back the noise, and you kind of compare and look at that the noise carries the watermark. So this is great, though it's too slow, right? Because for like state-of-the-art diffusion models, you need GB300s, like ideally a cluster of them, even just for the inference. It takes like a couple of seconds to do the inference for one image. So to do the detection, also need these GPUs also need that much time. So it's not practical. If you want to do it kind of in some kind of semi-open way, you cannot like go to Meta, go to OpenAI and tell them, hey, give us your Sora model. We want to detect the watermark, because you need the model that generated the content. Not great. Also, if you go to the teams that are responsible for delivering these models, and you tell them, hey, I just want to change your sampling process. I just want to inject something into your model. This will make the watermark great, and like everybody's be happy. They're like, no, no, no. Like we spent millions and billions of dollars on like training this model, and this is like our state-of-the-art model. We're not gonna be like hamstringing it because like you just made up some technique how to watermark it. And of course, it really doesn't work on the real content, because you kind of cannot add the bike to the to the content. It would like the original author who took the picture wouldn't like it, right? I guess. So in the end, maybe for the large scale industry applications, this is what we have. Maybe we need to stick with the post-hoc for now. So let me now present the PixelSteel work, which is a post-hoc watermarking solution. So it takes the original image. It has an embedder, which is a neural network that, besides the original image, takes the message you want to encode into the image. It watermarks the image, adds a small imperceptible change ideally. Then, when you are training it, or even in real world scenarios, that is people play with the image, they introduce some changes, and you want to still be able to recover this. When you are training it, you simulate these changes that people do, ideally differentiable, and then you train it using a message loss, which is just binary cross entropy, to basically train both the embedder and extractor to be able to embed and recover the hidden message from the image. Obviously, you need to put some constraints on what the watermarked image can look like. So normally you would add perceptual losses. If you look into the literature, there is every paper has like at least 3 losses, combination of 3 perceptual losses to make it close to each other and ideally imperceptible. That's why we don't do it, because it sucks, because you need those 3 different losses and it still doesn't work and it's still perceptible. So instead, we just use discriminator that ideally will make sure that the artifacts in the image are kind of the same distribution as the real world art or like real world images, and therefore it's difficult, especially if you just give out the watermarked image. It's very difficult to see any special artifacts. And of course, but we need to then manually limit how much difference the embedder can introduce, because obviously if you just do discriminator, it could still add the bike to the image, right? Theoretically, because you are not restricting now the embedder to produce something which is close to the watermark, to the original image. Okay, so in detail, how the embedding works: you have the original image for the pixel seal. You need to resize it to a fixed resolution and predict the raw watermark. So the model doesn't predict the image, a watermarked image, it predicts the raw watermark. Then this gets upscaled to the original resolution, but this is now with a lot of kind of artifacts after the upscaling. So what you want to also do, or what we do, is we kind of compute this just noticeable difference, kind of basically it's glorified edge map, to basically attenuate the watermark only to the areas which are ideally less visible to a human eye, so basically to the edges. We also have this like alpha scaling factor to make sure the watermark is not deviating, or like the added watermark is just adding small change to the original image. How do we train this? So we train it in multiple stages, actually. So at the beginning, we don't use, well, as I said, we don't use any perceptual losses. We don't even use discriminator at the beginning, and we set the watermark strength high. So to basically make sure that both the embedder and the extractor can embed and extract the message. So we can see the bit accuracy goes to 100%. Obviously, the visual quality is very bad. You can see it in the image. There is like a lot of checkerboard artifacts, and I think you can see it easily through the zoom and through the projector. Then we add the discriminator. Now the image looks much better. There are still, for the trained eye, you can still see kind of some vertical stripes in the image, but it's much better. And then in the end, we slowly decrease the watermarking strength so that we limit basically what the watermark can add to the image, and this makes ideally imperceptible watermarks, and then we can potentially find you additionally. Okay, so now how do we do detection? Suppose that we embedded a watermark, in this case all once, to the image. We extract the watermark using the extractor, and we end up with 250 ones and 6 zeros. So because the model actually, the pixel seal model embeds 256 bits. So this is probably actually our detected, our embedded watermarked image, because we would assume that in general, if we take an image from the internet, there's going to be half of the bits are going to be matching, half not, right? It's just binomial distribution, and based on the binomial distribution, we can even give like a theoretical FPR. We can basically compute a p-value, how likely it is that that message was like just generated by chance. And of course, if you have 250 bits matching, then the probability that this is by chance is basically 0, right? It's like so many zeros. Okay, so this was how to detect. Now how to measure the performance of the model. So this is actually very difficult, because we have these like different trade-offs. We can make the model very robust, but then the watermark is going to be visible. We can make the watermark very invisible, but it's not going to be probably very robust if you like use strong JPEG compression, you do cropping, or then for video, for example, you use video encoding. It's not going to be robust. Third axis is probably payload. So if you want to be statistically very much significant, you want to add bigger payload, right? So that like you have more statistical significance in your test for the detection. But then obviously more bits you add, you need more capacity. So you decrease robustness, you decrease imperceptibility. So there is this trade-off. For Pixel Seal, we fixed the payload to 256 bits. So we like mainly care about imperceptibility versus robustness. So this is actually kind of the graph for the Pixel Seal models. On x-axis, you have imperceptibility measured as PSNR. It's like very bad metric, but just to give an idea, basically any metric for visual quality is bad metric, but And then on y-axis, it's the robustness. So you can see you can pick very robust model, but it's not going to be that imperceptible, and vice versa. So that's kind of this ideally Pareto optimal front where you want to be with your model. And basically, where to be on the Pareto, or how to choose the kind of the optimal point on the Pareto curve, it's up to you, right? It's depending on application. But how to do it in our setup, you would think maybe different weights for the losses, increasing the weight for the discriminator to make it less perceptible. This doesn't seem to work great. It actually doesn't work at all, basically. Very, very, very little. So what we do instead, and what works great, is we do what we call watermark boosting. So for the discriminator, we don't give the watermarked image directly. We basically boost the watermark, and we give more watermarked image. And so for the discriminator, it's easier to see the artifacts, and this will make it easier for the discriminator to also get rid of them. And vice versa, you can reduce it to make the discriminator less powerful and make the watermarking more visible but more robust. Okay, so this is a video, and watermark for the video. It's through the zoom. I'm not sure how smooth it is and how visible it is. But yeah, so basically the watermark is tracking where the edges are mainly, right? That's kind of what it has been trained to do. Okay, and now basically the model that I talked about was just image model. So how do we adapt it to video? So a simple solution would be train on video, right? This is actually quite difficult. First of all, it's very compute consuming. It's much more difficult to train on video than on images. And also, it introduces a lot of unintended artifacts. So if you add 3D convolutions or some attention into the model, then the model tends to try to find shortcuts, such as putting all the watermark on one frame and ignoring the others. So for this, we just train an image model, and then just for the inference, we add temporal pooling layers into the UNet network, and then unpooling layers, so that the high-level layers in the middle, they can compute on lower lower temporal resolution, and then the fine-grained detailed layers that producing the pixel-level artifacts then can work on all the frames. And this actually works basically with no loss in performance and speed up depending on where you put the temporal pooling into the network. For audio, you basically do the same. The only difference is that you use waveform or MEL spectrograms, and you kind of end up with similar models. So this has been the audio, image, and video. How do you do text? That's a bit more problematic because text is discrete, right? So actually, there is a lot of watermarking methods for text. And basically, they are all based on the fact that the LLM is producing a distribution for the next token. And you sample from it. And when you want to watermark it, you change the way how you sample. And that's how you then also detect the watermark. So the most simple solution for watermarking is based on this Gamble trick, Gamble softmax. And it basically, what it amounts to is that sampling from a probability distribution is equivalent to getting a random vector R and doing Rmax on R to the power of 1 over P. This is, if you choose random R, then you, for different random Rs, you then in the end sample as you would sample from the distribution P. And if you want to watermark this, you don't choose R completely random, but you use pseudo-random R that is based on the previous context. So this will basically define this pseudo-random context, and the pseudo-random R will define which, with the distribution, will define which token you sample. The issue of this is that while it's equal to sampling from the distribution P, it's deterministic. And for the large language models, this deterministic property is a bit problematic because you can end up in like reasoning loops, or you end up in a loop, and the model cannot escape from it because the content is the same, the probability distribution is kind of similar, and because it's deterministic, then you don't allow for random chance in there. The model can get into loop, and so this can potentially hurt performance, even though it is equivalent to sampling from the random distribution. Sorry, from the softmax distribution. So what we do with text seal, we make it non-deterministic. How do we make it non-deterministic? We use two different vectors, two different hash functions, basically, to select the next token. And we randomly switch between these two. And yes, did I change the order of the? Yeah, I changed the order, sorry. So how do we detect that the content is watermarked? For the standard Gamble watermarking, you have the R, and so you basically add the value of the token, like the vector R for the token that you sampled. So for this, you need to know the tokenizer, and the hashing function, but otherwise you don't need to know the model. You just need the tokenizer and the hashing function. And this way, you basically count the R's, and because the R's normally would come from a normal distribution, the sum of R's would come to a normal distribution, you can check that in your case, if the text is watermarked with your key, it's not going to be following the random distribution. It's going to be out of distribution, and then you can get, using a z-test, you can get p-value for the detection. And for text seal, it's kind of the same. The only thing that you do, because you have two different vectors, and you don't know which one was chosen during generation, so you basically add the two together, the two scores. This is not as robust. Obviously, the p-value is going to be slightly decreased because you are diluting the information. So what we do also, we do entropy weighting for this score. How it works? Ideally, well, you get this. If you have the distribution of the tokens, you can compute the entropy of that token. And if the entropy is high, then you give high value for the score. If it's low, then you give low value, because basically then the sampling is deterministic no matter what your key is. And this will significantly improve the detection performance of the watermarking. The issue here is, how do you get the entropy? Because you don't have access to the GPT 5.5 model. And also, when you are doing the detection, or maybe you have the access to the model, but like doing the detection by running the LLM is very costly. What you can do is you can take very 2B model, a very small model, open source model. It doesn't have to be from the same family. It can be basically trained on different data. The entropy estimation, the general entropy estimation works, and you can use this small model as a proxy to get the entropy estimate on your tokens. And so if you do this, you end up with something which is quite diverse. You can see that Gamble Max, that's the star. It's not diverse at all, right? It's deterministic. Whereas TextSeal in general is very diverse. Maybe SynthID in the extreme, SynthID watermark that like is a bit more complicated, is theoretically more diverse, but TextSeal is more detectable. And with the entropy weighting, it's even way more detectable than the Gamble Max. It's also detectable under dilution. So if you add a lot of text around your watermarked sentences, it's still gonna be detected. And as I was talking about, that sampling from the softmax distribution is using argmax. This gamble trick is the same as sampling directly from the softmax distribution. It's actually like verified even in practice that it doesn't decrease any performance compared to like if you know, for example, green red list watermarking where you bias some tokens and so the final text is not distortion free and you can potentially degrade the performance of the model. Okay, so this is it. Do we have time? Do I still have a couple minutes? Okay. So maybe what are the problems, the current problems, and what we should work on? So I talked about this imperceptibility, robustness, payload trade-off, but actually in practice, it's much more complicated, right? You need speed. Like the models need to run on like any hardware on servers. Potentially you want to, if you want to watermark real content, it needs to run on devices, on your phones. It needs to be adaptable to new models, new architectures. There is obviously the security side of things. And so because of that and because of these problems, as I mentioned, basically there are a lot of roadblocks to using something like tree-ring or these like even we at Meta, we did like some work on watermarking autoregressive models. Image generation models, this is not like that much practical for the real world use case because of these issues. So that's why people, at least at Meta and Google and so on, basically use only posthoc watermarking. But the posthoc watermarking comes with the main downside that even though it's robust to real-world modifications, unintended modifications, the unintentional modifications that users or like social networks do by themselves. If you want to target, attack, and basically remove the watermark, you basically always can. Also, now with the legal requirements, everything, all companies need to watermark content, but the detectors are, every company has its own detector, every company has its own embedder, and obviously especially the embedders, those are proprietary. You don't get access to them because if you get access to them, you can basically give any content as legit as like coming from the company. So this is secretive, but maybe if there would be a way without revealing the embedders to get a single shared extractor so that all companies and like potentially everybody can use it. And this goes like one step further. It's like, can we actually make a posthoc or in general any watermarking model that can have a public detector or like even through the API now. Like if you have the detectors through API, which is the case of SynthID, soon for Meta, there you can probably try to exploit it. So that's also the reason why those APIs are very rate limited, and you can ask a couple times a day, and you cannot like scrape it and try to evade it. So the key takeaways from the presentation that basically content provenance is required by regulators, but has actually significant revenue creating potential. For example, for the content protecting and stuff like that. Posthoc on this scale and in industry is kind of the solution to go because of its flexibility. And then obviously there are new and exciting problems around security and this cross compatibility and detection that we are working on and you should work on as well, hopefully. And like maybe we also do have some internships and postdocs. So look at Meta website. And if you want to join Paris team, we would be happy. This is linked to our maybe not super up-to-date website with some of our works. And yeah, that's it. Thank you very much. Happy to answer any questions if you have time. If don't, then I'm sorry.
This is the microphone for the questions, so now I can embarrass.
So my question is, have you tried removing the watermarks, and how hard is it?
Yes, we actually do have also some papers on removing the watermarks. It is depending on what information you have, right? I can say that I was surprised that actually the model that is supposed to run in production in Meta basically like today or a week from now is actually quite robust to like those basic attacks such as like watermark averaging and spoofing, even if you have like white box access to it. So, but yeah, so we'll see.
Okay, so I suppose that's much harder than removing metadata from the file, right?
Yes.
So that's the point.
Yes, that's the well. We are still that what basically I showed in the slide. We are targeting basically unintentional modifications. If you really want to remove it and you know what you are doing, you're gonna always remove it. But yeah.
Cool. Thank you.
More questions? Oh, sorry.
Go ahead. It's fine.
No formal guarantees. Right. So for text seal, the thing you did with Gummel maxing was essentially say, instead of just using one key, we're gonna use two.
Yeah.
My question was, have you guys explored using more than two, using different categorical distributions, different weights? How does that affect the performance, if at all that has been tested?
Yeah, great question. Actually, we have George from University of Maryland now working with us, and that's exactly what he's working on currently. Basically, the idea is more the keys you have, the less detection power you have.
Yes.
So that's kind of the short answer, but it's being like now we are looking into it. But yeah.
Okay, I got it. Thank you.
Any questions? No questions? Thank you very much.
Thank you so much. That was great. All right. So wheels are vectoring. And I think now comes the moment that you all have waited for, namely the disclosure of the tasks.
Okay, so
I think like, do you share the whole screen on Zoom? I think it's not shared on Zoom yet. So Zoom. Here's the Zoom room, and then we now need to only find the mouse, and then
share the audio.
I think like audio we don't need to share. There's no audio in here. No, I don't see the mouse.
It's here.
Okay, perfect.
I'll just put it here. And 62.
Yeah, very good. Awesome.
Okay, everyone. So now is the time to share with you the tasks for this next 24 hours of the coding and hackathon. So Thomas talked to us about different watermarking schemes, including text seal. And actually, the first task is about text watermark localization. So let me first start from the background. So Thomas talked to us about couple of watermarks. We talk about gamble marks and text seal. However, here what we will also exploit in this task actually is also the watermarking based on the red-green list, also was mentioned here. So probably most of you already are familiar with this watermarking scheme, but briefly, how it works is that we generate the next tokens by, in this case, LLM, and then we would like LLM to generate tokens primarily from the green list. So we nudge the LLM to generate the tokens from the green possibilities. And to give an example, if you have text which is no watermark, clean text, you have roughly same number of green and red tokens. However, if your text is watermarked, then actually most of these tokens are from the green list. Now, yes. So just a brief recap how this works. So first we start from getting probability per each token, so in the vocabulary for a given LLM. And then we use previous token to generate a random number. And then this is actually used to seed our generator to split the red and green lists. And finally, you sample tokens, you nudge the model to generate the tokens from the green lists. And then if you have to find out if a given text is watermarked or not, what you do actually is a statistical test. And as we mentioned, on average for the clean text, we have some number of green and red tokens, so no watermark. We have primarily, mostly, significantly more green tokens, actually the text is watermarked. So your task, number one, is to identify watermarked text regions. So if you have this text, then the green tokens are non-watermark tokens, meaning that the text is coming from natural content or something we don't give you as watermark. And the red tokens actually denote the watermark text with one of the 4 watermarks. So your task is to detect where in this given document, we have many of these documents, where this text is watermarked by one of these 4 methods. So Thomas talked about text seal and the gamble marks. Also in this task, we use unigram and this red-green watermark. So this is what you have to detect being in the document. And then what is the clean, meaning non-watermark text is, for example, human created, so no watermark. Also, we have no watermark text generated. And also as the, I would say, to even higher, to have a higher challenge, we also actually have different watermarks that are not from the above 4 watermarks. The text in green might be still watermarked, but not coming from these 4 watermarks. And then how you really perform the task is that for each token, you have to assign a continuous score in the range from 0 to 1. It's a score given per each token. So for example, if we have, let's say here word, the token stop, you give a specific score from 0 to 1, and same for the next token being 30. And the score which is above 0.5 or equal 0.5 indicates that the token comes from the watermarking scheme. If the score is below 0.5, this actually means the token is clean, meaning not coming from the watermarked region. So how do we assess the final solution that you provide to us is that we compute TPR at very low, in this case, 0.1% FPR. And what is given to you is a data set with 1,500 text documents. We have a training set with 90 documents and validation set also with 90 documents. And then for you, we provide test set with 1,320 documents. So what is the format of the training and validation sets is that we do have document ID, text, So the text which actually is a human readable text, token ID, token pieces, and the statement. Sorry. Then actually the labels. The labels actually are for the tokens. If token comes from watermark, you have label 1, otherwise label 0 from the clean text. And also we provide to you this test set. And here your task is to assign these scores for each token in the test set. So if you would provide to us the solution, this will be the format of the solution. So you have document IDs and then the scores for each token in the given document. Any questions regarding task 1?
So I have a question, because you said that there are 4 determined watermarks.
Right.
And if my question is, if there is watermark that is not from list of 4, then do we be mounted or
No.
We don't know from which watermark it's been.
Yes, in this case you don't. So we only give if it comes from one of the watermarks, 1 or no, but we don't provide information from which one it comes from. Okay. No more. Okay, one more question.
Like classify from which watermark?
Exactly. So you,
Is it watermark?
right. We also will give to you information how we watermark the text. So of course you have these 4 watermarks which are very much specific. So we give you information about how we watermark this text. So in principle, you should know which watermark was really used to classify correctly the given token.
Right. So how much do you care about the confidence that we have in our predictions? Can we be overconfident that, hey, this definitely, absolutely has to come from a watermark? And is that okay if it actually comes from a watermark?
Yes. So very good question. So this is why this score actually is from 0 to 1. So and also why we have this low FPR. So if you're not confident, better you don't put this score too high, because otherwise we'll punish you with this score being at the low FPR. So here actually your confidence. So actually you can think about this as a confidence, that this score from 0 to 1 is a confidence how much you think that the given token is coming from the watermark region, right?
Makes sense.
Okay, perfect. Any more questions regarding task 1? No. Okay. Yes.
Is this task 1 or task 3? Why is this task 3?
What is task 3?
Doesn't matter.
Oh, sorry. It's task. Sorry. We have a last minute change. Okay. Okay. Sorry. So I think that this is a good observation. I didn't change everything everywhere. This. Sorry for that. Okay. But watermark. Yeah, watermark actually is task 1. At least in the scoreboard, and we try to keep it consistent. Apparently, not everywhere. Okay. So if not, no more questions. Okay, no more question.
Is it guaranteed that training set, validation set, and test set are all balanced in terms of true positive and false positive? Like ratio is same on all the sets?
So you have basically the train set and the train set and the so here for the trace and the validation set you have perfect score. So you have ground truth, right? So here the TPR is 100% at any FPR, right? So we have ground truth.
Okay.
Now your task is to provide the labels or the scores per token, and then you compute your score, right? So sorry, and then actually compute the score that you will get for this task.
Okay. Okay, I asked because I was wondering if it could overfit accidentally.
Well, I think that if you overfit, then it's okay. Overfit to the scoreboard, maybe. Yes, you can, of course, overfit the scoreboard, but we have the same thing as in every single competition. We have also 30% in the scoreboard of the results, and 70% is left for the final validation. Okay. So I think we'll move on. So now we can talk about.
Yeah, I have questions. So regarding like the overfit problem, what will happen if we will submit like the solution which will be more overfitted? So on the scoreboard, we'll see this one, the more overfitted version. But what if we wanted then to decide to push another version which will has less score but less overfitted? Would it be possible to replace that model?
I think that now we enable that in the scoreboard that you can actually submit it. So Aditya, just to confirm, in the latest version, do we allow to submit solution that which potentially has lower score on the scoreboard but can generalize more? I think that we enable that in the latest version, so it should not be a problem.
Thank you.
There's one more question over there.
Which one?
So just one more question to make sure that we understand how actually you score. So basically how we assign is the confidences of each token, right? That it comes from watermark versus non-watermark. And then for the comparing it to the ground truth that you will evaluate later on, it means that everything more than 0.5 will, is there a, how does it work?
So ultimately for the score, because it computes a TPR at the low FPR, it will actually set up the threshold so that you will get the highest possible.
Okay.
Yes.
Okay, got it.
So it's kind of how we just signed it, but yeah. Okay, so we can move on. So task number. Okay.
Do we get the best score or do we get the latest score?
Yes, so you will get the best score. So if you submit a solution that performs better, then actually the solution is in the final validation set taken as the last one. So basically, so in our scoreboard, we take your best possible solution for the validation set. So don't worry. Okay.
So basically, if we do that, if I come up with a more robust solution, which doesn't perform really well on validation, but I'm confident that it will perform nice on test.
So I mean that we give the best solution that you will have on the final validation set that is not reviewed in the scoreboard. The test set, yes, validation test set, yes. So not leaderboard solution, but the final solution. Okay. So let's move on quickly. So as you know, nowadays we can generate everything with models. They are trained on everything. So they're trained on books, newspapers, music, codes, images, and much more. And also these models can generate everything from complex text to photorealistic images, as you saw with the fake news. And what's more is that we also showed in our group that these models can memorize individual samples. So it was shown that models like Llama 3.1 can memorize the whole books, like Harry Potter book. Also models like Stable Diffusion 1.4 memorized the whole images, like face of this woman. And then after memorization, models actually generate the same samples verbatim at the inference time. And this really led to many copyright and privacy violations and many lawsuits. As of now, there are more than 100 lawsuits, and this number grows really fast, and with claims of over 100 billion euros. So this is a big issue. So of course, as you also heard, we have fake data, fake news. You can generate literally everything with these models. And what's more is that now we have this problem that the inputs to the models are blurring with the outputs, meaning that quality of outputs is so high that you basically see these outputs as being natural data. So this actually causes data loops that models are trained on generated content. So we generate a lot of data from these models, then we publish them online, and models actually are then used or trained new models on the data which is scraped from the internet, which is also generated. So this causes these data loops. And in the long run, if you have this many new data, which are, for example, with incorrect values or with some fake information, it actually causes that the models degrade in quality. And what is the task for you today actually is called our new task, which is member versus generated inference, in short, MGI. So here we have data like M and N. Actually, M data is a training set for the model M1, and the green data is non-member data, but also being natural data. And the model M1 generates new data. So this is known as G. So model G generates data, and so can also even go further. So also model M1 can generate data which actually is not used to train new models. But you have also new models like model M1, M2, M3, and so on and so forth. So they can also be trained on the generated data from previous model versions, for example, from model 1. And you have this basically data loops that models generate new data and it's actually reused to train the new models. The task for today is a bit simplified, but different from just finding out where data comes from. But here, what we have, so what we designed in our lab and created was the detector to detect whether data actually is non-member, member, or generated. And then in this task, we ask you to actually fool our detection method, to design a method that actually can then fool our detector to classify member samples as non-member samples, member samples as generated samples, and non-members as member samples, non-member as generated samples, and then G as M and G as N. So we ask you to basically be an attacker, be in an attacker's shoes, and pull out detector to be able to change the data slightly to fake them as being, for example, from members to being non-members, or from members to being generated. And what we are given to you, what we give to you is set of 900 samples. So we have 300 members, 300 non-members, and 300 generated samples. This is given to you. This is your starting point, and you have to start from these samples to generate these faked other sets. This is the full submission format. So as I described, you have to fool the detector, and you have to provide all of these different number of samples for the fooling of the detector. And now, how do we assess your solutions? So first is detection score. So 1, if sample is misclassified as intended. So for example, if you start from the member and you change to non-member, then you get 0.1. If you're not able to fool this detector, then you get score 0. Now, also we care about image quality. So if you have image I, naturally we compute mean squared error for the image I, and this basically is standard mean squared error. So first initial image X minus the modified by you image X prime, which should be fully out detector, and then divided by number of pixels in this given image. And then finally, we assess your all 800 submissions of these images, and we compute this score. So basically, the best score is 1 if you fool the detector, and actually then we have here the term, which is assessing how much you modified the image. So the less you modified the image, the higher the score. Any questions regarding MGI task? Yes. hard to throw. Okay.
So I wonder, you had like from each category, 300, like from M needs to go to both N and G. Is this considered in the score, or we could do like 600 of M to N and none from M to G? Okay, so you actually, because I don't see it in the scoring, right?
It's 1800 number of images with others and
But it's enough to just misclassify it, not that I need to misclassify 300 into two different categories.
Yes, please target it. So you have to specify so if you are given 300 ends, each of them actually has to be changed to non-numbers, each of these 300. And it's the same actually for the G part. You have to, so for each of these 300 ends, you have to change them to be generated.
Okay, thank you.
There's
a question, what type of access we will have to the model? Will it be black access or black box?
So actually we give white box access, right?
yeah.
So you have full access to the model.
Okay. To the detector or to the, yeah, that one's to the model. Okay. For this task, the output has to be an image, or it has to be it's just from member to a non-member.
You have to provide to us the image itself.
Okay.
So for each of these has to be an image that you provide. So you have to basically upload these 1800 images.
Okay. Okay. Yeah.
What is the format for the submission?
So exactly these 800 images, you submit them, and it has to be in this order.
Okay.
So, for example, if I in the first image, how do you check if I, instead of taking from the M set, I just take them from the N set, for example, to.
That's what the MSE is for. Like, so
Oh.
it like will look significantly different than the image, like the first one of the members.
Okay, okay.
There's a question in the back. Do you just want to pass the cube up or throw it up, or?
It really was.
Right. So I might have missed something, but do we have a resolution on the images? Like, what resolution are we working with here?
I think it's a 64 by 64. Ima, what is the current one?
Oh, okay. Okay. Thank you.
256 by 256.
Got it. Who do I get this back to? All right.
No more questions.
Are you awake now? So, okay, so then let's come to the next part, which is still yet in another area of machine learning, namely the aspects of privacy. Because I think each and everyone here in the room generates lots of data, whether we take photos or write messages. And even if we intend those to be for our friends or family, like for example, Alice here does when she takes selfies, what happens in the background is often that companies train their machine learning models on that data. And there are two ways how you can train such models. One is in a centralized way where the server collects all the data. And what you directly see here is that the server has to store Alice's data, and thereby basically her privacy leaks directly to the server. As a solution to not have such a direct leakage of the data, federated learning has been introduced, where the server only instantiates a model and sends that model out to all clients, and the clients do the training locally on their data. So they calculate some model gradients, and then they send those gradients back to the server. The server aggregates all of them and applies them to the model. And because like the data is never sent to the server, federated learning has been long marketed as a privacy preserving technology. However, if you look at this picture here, what you see is that like you have all these users, and you have Alice, and the only thing that stands between Alice and like her data leaking to the server are the gradients. So the implicit assumption here is that gradients should not leak private data. And in this like challenge, the last task here, you're going to put yourself in the shoes of an honest but curious server and stress test that assumption. So you're passive, honest but curious. You cannot manipulate the model itself, but you want to extract the data from the gradients that you get from users like Alice. So what we'll be providing you with are gradients from 12 different models, and that have been basically used to train with federated learning. And each of these models was provided to different 12 users, like Alice, who generated the gradients from their private data. And each user has locally 128 private images to calculate these gradients on. So this yields a total of 1,536 private images that were used. And your goal is to reconstruct these 1,536 images as accurately as possible. And what you will basically be submitting is the respective images for each model. So the 128 images, which are each in the dimension 3 channels, so it's a colored images times 64 by 64 pixels. And like the pixel values are each floats in the value of 0 and 1. And so basically your like submission is this tensor where per model you have this 128 images, and like you just upload those images. And the score that we will be calculating is over the whole data set, namely the SSIM score. So the SSIM score is a structural similarity score. So we'll be taking the average, like it measures basically how similar your extracted image is to the original images. And we'll be convert this final score, the average SSIM score over all images from all models, into the range of 0 and 1. And so like there are no submitted images that are like the same, so like duplication will not achieve optimal results here. Yeah. Are there any questions about this task, about the data that you need to reconstruct from the gradients? There's a question here. Sorry, you're sitting again in the line, so I'll try to be careful.
Which data can we access? How do we access the information we need from the federation?
You don't need federation, you're just like the server, you get a gradient, and from the gradients you extract the.
Okay.
So the different images that you get from the different clients in the federated models, like they are they are not independently like generated. They are from the same dataset, or
You don't have to make any assumptions on the distribution here.
okay.
Do we know like the federated learning design choices behind the models, like which federated round it is, or do they all have like the same federated like settings for all the models?
You don't need the knowledge on that. You just get the gradients and can do the extraction from there. Any more questions? Exactly. Each client provided 128 images. Yeah.
You should go through Juliana, I suppose.
Oh.
Hello. Can you go back to the previous slide? Where do we have the metric?
Oh no, actually it's okay. The metric, sorry, the metric.
Can you, what is SSIM again? If you want to define.
You can put it like you can read up on it. You can treat it also as a black box and just say it's like measuring the structured similarity. But I would strongly recommend that you read up in the paper how the score is like defined, because then you can probably extract with more fidelity.
Okay.
Okay. So also regarding the infrastructure, so
We
it's
can keep it short, right? The
yes,
same as
yes,
always.
it's the same as always. I think that not all of you are there, so please also send the requests, and I will accept your request to join these servers. So as usual, you can work on the servers from Ulis, and this time we have project 2625. I send the link also on Discord, so please click the link and okay, get the access to the server so you can work on the tasks. But it's the same as always, so you have the same access to Ulis with all of these servers to work on the tasks. So any questions still? So if not, actually we have very soon we will have to draw for the tables and the desk where you will be working on as the teams. So Julian has the distribution of the desks. Also, we'll send to you very soon. Francisca will also set up the API keys as usual. So you also get them by email.
Yes.
And then you can get started. Good luck.
There's one more question.
Okay.
Tasks themselves, for instance, presentation, in Discord channel.
Yes, everything as always will be provided fully on Discord.
Okay.
Thanks
Perfect.
to the folks up there then.